topic. So, well, the main goal is to, I don't know, like briefly introduce what this domain is about and what is like the main question, and well, briefly discuss the state of art, including, well, the recent result which we obtained in this lasso ramp. And also, I think it might be helpful because during the week of the workshop, there will be like, I guess, several talks related to this domain. Okay, so yeah, today we are mostly going to talk about meromorphic maps, and I'm going to recall one notion that has been already introduced in Phil's talk. So I'm going to explain what are singular values of a meromorphic map. And to talk about singular values, well, I need to introduce what is a regular value of a meromorphic map. So I say that W is a regular value of our map G if, well, which is a point in C hat, if we can find a neighborhood of W, some neighborhood U. So if you look at its preimage by G, well, we have a bunch of connected components. And well, we call W a regular value of G if restricting G to any of this connected component of the preimage, we are getting a homeomorphism to the original set. So informally speaking, it means that we can define kind of inverse branches of G in the neighborhood of this point W. And well, if it's not the case, if we cannot find such a neighborhood of W, we call it a singular value. So those are singular values, we denote them by S from G. Some examples. Well, first of all, if our map G is just a rational map, well, singular values and critical values is the same thing, so no problems here. Well, if you go to transcendental world, there is one more type of possible singular values. Well, if you look at the exponential map, well, it has no critical points, no critical values. However, it has one, well, at least one a singular value. So if you look at 0 and we take a small neighborhood of 0, its preimage is going to have a single connected component which is mapped with infinite degree to the original set. So those are called asymptotic values, and you can really think about those like kind of critical values above a critical point of infinite degree. So really you should think, if you're, well, kind of uncomfortable with transcendental stuff, you can think about singular values as like the analog of critical values in the transcendental world. Yeah, and well, kind of space of all meromorphic maps, if you want to study its dynamics, is like kind of a normal space, so that's why we want to restrict to some like reasonable large subclasses. And today we are going to talk about well, meromorphic maps of finite type. So sometimes they are called also like Speiser class maps, and they're denoted by capital S. So we say that such map is of finite type if its singular set is a finite set. So it's a, well, a large class of maps, which is, for instance, much larger than rational maps. It has many other kind of explicit maps in this class, but kind of in a certain way, most of the maps in this class, they have no nice explicit closed formulas. And well, and the nice thing about this class is that, well, kind of, we now know a lot about dynamics in this class of maps. Well, probably, well, for instance, we know that there are no wandering domains in this class, right? But especially in like last decades, there were several results obtained that were kind of, I don't know, mimicking properties that we have for polynomials, but in this much larger class of maps. Well, but there is one result that we have for rational maps, which somehow is still resistant to be generalized to this setting. And well, this result is Thurston's characterization of rational maps. And yeah, so we are still missing this result for this class of maps, and this is kind of main direction of my talk. And well, first of all, I'll say a few words about Thurston's result, kind of informally. So it's basically related to the following informal question. Suppose that we have some kind of dynamical system of topological nature, meaning that it's induced by some kind of, I don't know, continuous open map, not a holomorphic, not a smooth one. And we may wonder whether this kind of topological dynamical system is equivalent in a certain dynamical way to a holomorphic one. And kind of why this question can be interesting, because sometimes you want to construct holomorphic dynamical systems with desired properties. But sometimes it's difficult to do it, but it's kind of, usually it's much easier to construct dynamical systems with desired properties in the topological setting, because topological maps are very, very flexible. So, and then we say, okay, we have a topological dynamical systems with desired properties. Maybe it's equivalent to some holomorphic one. And well, Thurston gave an answer to this question in a setting of post-critically finite rational maps. So somehow I expected this, like up to this point, somebody will introduce post-critically finite rational maps, but I don't know, I hope. Yes. So yeah, but those are just rational maps where every critical value has a finite orbit, so it's periodic or pre-periodic, and well, you kind of know that this is relatively large. Well, it's structurally important class for rational maps, but at the same time they are nice, so it was kind of nice, natural class to look at. So Thurston showed that if you have something called post-critically finite branches of cover of two-dimensional sphere, so it's kind of plays a role of this topological dynamical system. It's in a certain dynamical way that I'll introduce in a few minutes, is equivalent to a holomorphic map, or an algebraic map, post-critically finite rational map, if you don't leave, there are no kind of multi-curve abstractions, which also I'm going to briefly discuss in a few minutes. So basically, Thurston, like in the context of post-critically finite rational maps, he kind of explicitly described what are abstractions for this object not to be realized by a holomorphic one. And yeah, we want to have the version of the theorem in the transcendental setting. Well, I guess the first question to ask is like, okay, in the transcendental setting, what is the class of holomorphic maps to look at? And those are called post-singularly finite, meromorphic or entire maps. So yeah, there are some examples, but essentially what we want to do, if you have a meromorphic map, we can look at singular values of this meromorphic map, the ones I have introduced before. And we can look at post-singular values, so we can just take and iterate singular values. So these are post-singular values. And well, we say that this meromorphic G is post-singularly finite if, well, all the singular values have finite orbits. Okay, well, if there are finitely many singular values and each of them have a finite orbit, so it's, So it's exactly, kind of obviously such map should be a finite type map plus orbits of singular values should be finite. So there are some examples. So there is some entire map. It has, well, if I remember correctly, 1 is an asymptotic value which is mapped to a -1, which is a repelling fixed point, and 0 is a critical fixed point. And there is some other map. Well, you can notice it is not meromorphic, because essential singularity is at 2, but it's conjugate to a meromorphic map. I just chose nice coordinates for this map. So it has one asymptotic value and two critical values, and all of them eventually land to 1, which is a super attracting fixed point. So in fact, there are in a certain way, there are more post-singularly finite meromorphic maps than post-critically finite rational maps. So it's a large class of maps. And basically, well, we want to understand whether we have analog of Thurston's result for this class of maps. And I guess, well, the first thing that I need to do is to kind of introduce this question in more kind of formally and give some definitions. And I'm going to follow the following plan. So first of all, I'll introduce what are topological models for post-singularly finite meromorphic maps.
So you do assume that SG also is fine.
Yeah. So I mean,
in principle, you could require that only the first number of first iterations is fine.
Yeah. So I kind of, when I say post-singular set, I include singular set. So
Depending on the those playing follows and people do.
Right. Well, I think usually people include singular set and post-singular set. People sometimes not include critical points in there. So yeah, well, but anyway, yes, we need both of them are fine. So the first, I would like to introduce what are topological models. So like, and what is this notion of equivalence? How we compare dynamically like topological thing to a holomorphic one, and then I'll discuss what kind of potential abstractions for topological thing to be realized by a holomorphic one. Okay, so this is a plan. Any questions at this point? Okay, then I'll introduce something called topologically holomorphic maps. So if we have, let's say, two topological surfaces, and we have a map that admits the following nice, just kind of topological properties. So our map is continuous, it's open, it's discrete. Discrete means that the preimage of any point in Y is discrete, and the preimage of any point in Y is discrete in X. So it's just kind of, in a certain way, it's like all topological properties that a kind of generic holomorphic map between two Riemann surfaces has. Well, since we are interested in meromorphic maps, we are going to look at the maps that they are defined either on sphere or on kind of punctured sphere, and the image is sphere itself. Well, so for all this machinery to work, we need to add one technical condition, which I'm not going to discuss. But if you want, you can imagine that our map is, for instance, quasi-regular. And this notion luckily was introduced in the previous talk. So, well, all the quasi-regular maps are topologically holomorphic. And I'm going to use the following notation just to say that our map may or may not be defined on the whole sphere. Okay, so those are topologically holomorphic maps, and So actually for topologically holomorphic maps, we can introduce also notion of a singular value. Because if you look at this definition, in this definition we never use the fact that our map is actually holomorphic. I just said that something is a homeomorphism. So we can introduce singular values for topologically holomorphic maps, and in particular we can talk about post-singular set and so on. In particular we can talk about topologically holomorphic post-singularly finite maps, but we are going to call them Thurston maps. Well, for instance, because it's much shorter. And and that was essentially by the idea of Thurston to introduce those. Yeah.
So topologically holomorphic, weaker than branch cover?
Well, if our map is defined, if our map is defined on S2, then it's exactly the same thing. But the thing is, well, when you have a branch cover on like non-compact surface, people introduce branch cover differently. Somehow, for instance, I was talking like, well, exponential map, is it a branch cover or not from C to C? Like, so I would say, well, it's not a branch cover because in general it can have asymptotic tracts, and this is not something that usually we want to have. But like in different sources have seen different definitions. So, but when our map has no kind of essential singularity, when it's defined everywhere on S2, it is a branch cover. So I mean, this definition for a map that are defined on the whole sphere, this coincides with a kind of classical one. Yeah, and so how should we think about Thurston maps? Well, these are topological kind of models of post-singularly finite meromorphic maps. In particular, all post-singularly finite meromorphic maps are examples of Thurston maps. But if you want to construct an example of something non-holomorphic, well, take your favorite post-singularly finite meromorphic map, or well, post-critically finite rational map, and post-compose it with a homeomorphism, which preserves a post-singular set. So usually after such a composition, we obtain something which is not holomorphic, but it will be a Thurston map, it will be a post-singularly finite. Okay, so I have introduced like the topological versions of post-singularly finite meromorphic maps, and now I need to introduce the equivalence, what is the dynamical equivalence we will be talking about. And this is called combinatorial equivalence, and it has several equivalent definitions. And maybe this is not the most classical one. Usually people introduce it differently, but I'll use this talk as an opportunity to advertise this version of defining combinatorial equivalence. So we say that two Thurston maps are combinatorially equivalent if we can deform F to G through a continuous family of Thurston maps, so post-singularly finite topologically holomorphic maps. But also we require that in this deformation, all the maps, they have the same size of the post-singular set. Because if you have such deformation, well, singular values of our maps, they will move continuously, but they might collide. But we just say that we have, well, we can deform F to G continuously without collisions of singular and post-singular values. Yeah, so this is, and in fact, well, it takes a little bit of time, but you can convince that this is actually a dynamical thing. And for instance, if two Thurston maps are topologically conjugate by homeomorphism, they will be combinatorially equivalent. So it's weaker than topological conjugacy. Okay. Yeah. Yes.
So the last condition says that there are no collisions.
Yes. Yeah. So no singular, no post-singular values collide while you. So
it's like people say like Thurston equivalent. Is that?
Yeah. Oh, okay. Sometimes people call it Thurston equivalent, but there are too many like Thurston maps that are Thurston equivalent. Yes.
Makes more sense.
Yes. So yeah. So in particular, all these maps, they will have the same dynamics. Well, honestly, conjugate dynamics on post-singular sets, right? Okay. And yeah. So now, well, we can formulate the question that I stated before in mathematical terms. So I'll say that Thurston map is realized if, well, it's combinatorially equivalent to a post-singularly finite meromorphic map. So we can deform it to a post-singularly finite meromorphic map. So I said that Thurston map is realized by a post-singularly finite meromorphic map. Otherwise, if it's not the case, we say that our Thurston map is abstracted. And well, basically the question that I kind of hand-wavy introduced at the beginning is that if you have a Thurston map, when it's realized in the sense of the following definition. So and basically Thurston result answers to this question in the case when our Thurston maps are defined on the whole sphere. We have no they're in a finite degree, they're not transcendental. Yeah, and so now I'll briefly discuss what are possible abstractions, what can go wrong if you have a Thurston map, what can kind of prevent it from being realized by a holomorphic one. And so I'm going to talk about, well, some particular family of abstractions, which are called Levy curves. So what's, if you have a Thurston map F, well, Levy curve is just a simple closed curve and the complement of the post-singular set of our Thurston map. Suppose we have, well, five elements in the post-singular set. So I'll draw some curves. So in the definition we require this gamma to be essential, and I would like to explain what it means. So I'll just draw some curves on the sphere and the complement of our post-singular set. So here the blue curves are non-essential ones, because we kind of can take what it means. It means that we can take this curve and we can shrink it to a point by a homotopy in the sphere punctuated post-singular set. So this we can kind of shrink like this, and this we can shrink like that. But however, the red curves, they're essential ones. No matter, I guess it's not feasible for. Okay, yeah, I guess I just finished. Yeah, so the essential curves are the ones that are kind of, we cannot shrink them to a point if we move them in the punctured sphere. Kind of move them without passing through the post-singular set. Yes.
What about this blue curve, which has a point? It's can be shrunk to something arbitrarily small around the point.
That's a good question. So it's also non-essential. So because we can kind of shrink it to a marked point, but it's kind of still one point. So we still think that we still treat it as a non-essential one. So suppose we have, essential means interesting up to homotopy in punctured sphere. So if you have a essential curve, well, we can look at this preimage by our map. It will be a bunch of curves. And suppose among them we can find another curve gamma prime, which is essentially the same as the original one. So gamma and gamma prime are homotopic. And moreover, the degree, gamma 1 is sense to gamma with degree 1. So if you have well, if gamma satisfies all these conditions, we call it a Levy curve. And sometimes it happens that gamma is not a Levy curve for map itself, but it's a Levy curve for an iterate. So that's, in this case, we call it a Levy cycle. And it's a general principle that whatever Thurston map has a Levy cycle, then it's abstracted, and it's kind of generality, and it's, well, relatively easy exercise in hyperbolic geometry. But we can ask the kind of whether converse is true. Whether if you have an abstracted Thurston map, does it mean that it has this particular abstraction? Does it mean that it has a Levy cycle? And in a certain way, Thurston's theorem says that yes, this is the case. Well, we need, well, kind of Levy cycles are not enough. We have to consider some more general class of abstractions, but they kind of very close in spirit to the definition of Levy cycle, just is more technical definition. So morally, Thurston's theorem says that the converse is true. So if our post-critically finite branch cover is realized if and only if it doesn't have this kind of abstractions. Well, Levy cycles and slightly more general Levy cycles. Okay, and well, and then what's happening in the transcendental case? Well, in transcendental case, well, at least right now, we have no contradictions to Thurston's theorem. We know that it holds for some classes of maps. So here I'll just put, well, at least some results. I guess during the week of workshop, you might hear about other new results, but well, some results that are known at this case. So the first result was obtained in the work of Haber, Schleicher, and Shishikura, a few decades. So it took some time to kind of obtain first results in the transcendental setting. So they considered exponential maps, exponential Thurston maps. So exponential Thurston maps, it would be just the maps defined or R2 and having only two singular values, say 0 and infinity. So if you have a Thurston map which is like this, and it's kind of exponential. Well, from topological point of view, it's kind of exponential map. And well, if such map is realized, it would be equivalent to lambda xz, so like exponential family. So then similar method was extended to so-called structurally finite maps. I'm not going to define those. Well, those are maps with finitely many asymptotic tracks and finitely many critical points, whatever it means. But roughly speaking, then they look like the following family of holomorphic maps, which also, I guess, appears in Fieldstock. Yeah, and there were some other, well, methods applied that cover like maps that look like cosine or cosine of square root of z. And yeah, so I would like to mention that all these kind of restrictions, so they were taking some kind of families of maps and restrict to certain subclasses. They have function theoretical nature. So we say that, oh, our map, so there are no restrictions on the dynamics of such maps. They can have, well, whatever post-singularly finite dynamics, but it's more like on the function theoretical, non-dynamical properties of the maps. Well, and another kind of restriction that we can consider, we can look on the families of maps that can have like, well, pretty arbitrary function theoretical properties, but particular dynamics, and that's what I did in my thesis. Yeah, so basically we have a bunch of results for other restrictive classes of maps where Thurston's theorem is confirmed with different methods, but I think till this moment we don't know whether it's true in general case. Yeah, and yeah, I would like to talk about one new result in this direction, and I'll talk about first about so-called belly maps. So, and for a moment we'll stay in the setting of meromorphic maps, so everything's holomorphic. So we say that a meromorphic map is called a belly map if it has 3 critical values and no asymptotic values. So I recall that singular values for meromorphic maps, they are either asymptotic or critical, and we say only 3 critical values, no asymptotic values. Yeah, and I guess I should start by giving an example. So let's look at the following picture. So it defines a belly map where this will be kind of the domain of our map. It's complex plane, and this is the image of our map. So how we define this map? Well, we have this equilateral triangulation. suppose we pick, like, say, a black triangle. And we define our map on this black triangle to be a conformal map from it to the lower half plane, sending vertices to like -1, 1, and infinity. And we basically, well, we know that there exists, well, essentially one conformal map like this. And we define these conformal maps on every triangle. Well, like white triangle goes to upper half plane and black goes to lower half plane. And kind of, if you do it appropriately, it gives us a meromorphic map with 3 critical values at -1, 1, and infinity. And the critical points will be exactly the vertices of triangle. So it's kind of like, if you know what is Weierstrass rho function, it's like the same thing, but not using parallelograms, but triangles. Yeah, and in general, kind of these maps are related to triangulations. In general, how we can think about arbitrary map like this. So usually we can allow ourselves to assume that these 3 critical values are located at -1, 1, and infinity. And if you have such Belly map, we can take a preimage of real line. And it will be some connected graph, which will kind of, in fact, it will triangulate the plane. So actually, kind of in the proof of the theorem that I'm going to explain on the next slide, we think of Belly maps as about like triangulations, kind of triangulations of the plane. So here I showed some triangulation. It's actually given by a rational map of very high degree. So it's not a transcendental one, but when degree is very high, it kind of looks transcendental for me. Well, okay. So those are Belly maps, and now I will kind of state the theorem. Well, of course, we can talk about topologically holomorphic Belly maps. Similarly, we say there are 3 critical values and no asymptotic values. Well, and another notion I'll require is a bounded criticality. So I said that the map has a bounded criticality if it doesn't have critical points of arbitrary high local degrees. So we have a bound on degrees. Yeah, and so now I'll state the theorem. So it's kind of, I don't know, Belly meets Thurston. So we look at Belly Thurston maps with bounded criticality. And the theorem says that such Thurston map is realized by a post-singularly finite meromorphic map if and only if there is no multi-curve obstruction. So it's exactly the same thing as we have in Thurston's theorem, but in case of all these transcendental Belly maps with bounded criticality. Okay, so in particular, this restriction that on our class of maps that we have in this theorem is of function theoretical nature. So post-singular values can do whatever they want. Well, of course, it has to be post-singularly finite. And maybe in Romanian, I don't know, a few minutes. I don't know whether I have them, but so I'll speak about one feature of this result, which hopefully will explain that this is kind of pretty large family of maps. And so I'll mention the following problem. So if you have a meromorphic map, and we take its iterate, well, the map we obtain is no longer meromorphic usually, because some poles, they become essential singularities, and some prepoles. And also we know that, well, in dynamical systems, well, we sometimes have to work with holomorphic maps that they have relatively small domain of definition compared to its image. For instance, I don't know, we'll talk about Lavor's maps and these kind of things. And so, well, the question is, what is the natural kind of class of maps, kind of this partially defined dynamical systems we need to consider to kind of incorporate all these maps, especially when we stay in this setting of finitely many singular values. And kind of this question was addressed in the thesis of Adam Epstein. So he suggested that actually we can, instead of looking like meromorphic or entire finite type maps, we can look at much more general class of the just holomorphic maps depending on some open subset of C hat and having finitely many singular values. So once again, in this definition, I never actually use the fact that our map is defined on the complex plane. So we can look on the kind of this notion of finite type maps work for maps where the domain of definition is much smaller than the range. And again, for these maps, we say that they're Belly type maps if they have 3 critical values and no asymptotic values. And in fact, we can introduce like notions of Thurston theory for this class of maps. I haven't done it for like, technical reasons because there are some complications and so on. But the theorem that I have announced also works for Belly maps, even in the case when they are not defined on the whole complex plane. And this is a very large class of maps. For instance, quite recently, Chris Bishop and Lasse, they proved that, in fact, if you have any non-compact Riemann surface, for instance, you can have some proper subdomain of C, then it supports a Belly function of bounded criticality. So just some, examples from their paper. So those are some Belly maps defined by their triangulations. This, for instance, some Belly map on the unit disk, and this is a Belly map on the punctured unit disk. So in particular, our theorem, it covers maps that can be defined on arbitrary open subset of C, and which is kind of result of the first result having this new feature. So, and I think I'll stop here and thank you for your attention.
Or some belly map.
Mm-hmm.
Can it have more than 3 post-singular?
A post-singular? Or, no, well,
The size of post-singular.
oh no, post-singular set can be arbitrarily large. Even post-singular. Well, singular set is 3 points, but post-singular set, any finite number.
Okay.
Is there something special about, what's the distinction of having 3 post-singular set or points as opposed to 1 or 2?
First of all, there are no maps with 1 singular value. If you have 2 singular values, it's essentially exponential map, up to some precompositions. So for instance, if you have a holomorphic, say meromorphic map with 2 singular values, then it should be exponential pre and post composed with Möbius. So if you have 3, then we have, uncountably many parameter spaces. So it's kind of, so 2 is very special case, and it's essentially exponential map, but 3 singular values is already the whole world. But difference between 3 and 4 is that when we have 3 singular values, we can always kind of assume that they are at -1, 1, and infinity. So there is no kind of degeneration happening because of singular values colliding. But if you have 4, it's another feature adds. Yeah. Yeah. So bounded criticality is kind of important for the following reason. If you look at the space of Belly maps of bounded criticality, it's kind of closed essentially closed under taken limits. So if you have Belly maps of bounded criticality 5, in the limit you can have, with some exceptions, but you'll have basically Belly map is also with the same bound on critical points, on the number of, on the maximum criticality. For instance, it implies that if you look at the space of Belly maps with bounded criticality, all these triangles, they have kind of uniform geometry. There are some bounds on how angles can be, they cannot be arbitrarily small if you fix the maximal criticality. So there is kind of compactness in this space, yeah. Yeah. Spread out.
But you will need the bounded criticality, or you might allow something like growing criticality very slowly growing as well. It's combinatorially very far from the other set.
At this point, I would say that we kind of need it, and I'm not sure whether we can, how to allow unbounded criticality, maybe with some extra condition. I'm not sure. The problem happens when you have a limited of Belly maps, sequence of Belly maps, no asymptotic tracks, but in the limit, because of points with unbounded criticality, you are getting an asymptotic tract, and that's where problem happens. Yeah.
Is it a space in which you're acting finite dimension?
Yes. Yeah.
Or is
It's finite dimensional. So
Infinite dimensional if you have 4.
no. So the dimension of Teichmüller space is, well, dimension of post-singular set minus 3. So therefore, in this case we have 3 singular values, but post-singular set can be as large, it should be finite, but so we have to work with high dimensional Teichmüller spaces, but they always have finite dimension. So really,
Rates if you have 4 critical values?
well, one thing that becomes more complicated when we have 4 critical values, then that we have to control their position. Like if you have 3 critical values, we have map with 3 critical values, we can kind of assume that it has critical values at -1, 1, infinity. But if you have 4 critical values, we have them as, say, -1, 1, infinity, and x, and then somehow there is a new phenomena when 2 critical values collide. So when we have this kind of degeneration, and this is a kind of complication between 3 and more. So essentially, if you think about parameter spaces of maps with 3 singular values, they are kind of very simple-minded parameter spaces that kind of you say, okay. And if you go further, they kind of, yeah. So it's, well, I don't know. I hope it answers, yeah.
So you mentioned earlier this result by the first one, I think, where you said the Levy curves
Yeah.
the existence of this homotopy, right?
Could you say it again?
Are obstructions to the
Yeah.
existence of this homotopy.
Yeah.
Yeah. Is there a way of telling us why this taking place? That's like
No, in principle, okay. I think I can sketch it in a minute if you want. I don't know if I've... Okay. Suppose that we have a, let's stick to post-critically finite rational maps. Suppose that we have a SF rational map. Say it has 4 or maybe 5 post-critical points, and here I'll draw a post-critical set, and maybe there are some. So here I draw the post-critical set, and here I draw the whole preimage of post-critical set, which is strictly larger. There are some extra preimages. So if I take a Levy curve here, gamma, by definition there is a gamma prime, and the preimage, it has to be homotopic to gamma, which is mapped with degree 1. And what we can assume about gamma, we can assume that this is a hyperbolic geodesics in this puncture sphere. So it means that in, suppose that gamma, we have lengths of gamma in sphere minus post-singular set. And, if you look at lengths of gamma prime, it will have the same lengths in the hat minus preimage of post-singular set. Because, if we remove post-critical set from here, and we remove the whole preimage of post-critical set from here, our map F becomes a covariant. So it's a hyperbolic isometry. So the lengths of gamma, so we use the fact that gamma prime is mapped with degree 1. So the lengths of gamma in puncture sphere is the same as lengths of gamma prime in bigger puncture sphere. But then, which means that if you look at lengths of gamma prime in sphere punctured only at the post-critical set, if you forget these extra points, the lengths will get smaller, right? Because it's, inclusion is a holomorphic map. But we just assume that gamma is a hyperbolic geodesic. So we can find a curve in the same homotopy class with smaller lengths. But well, from like general hyperbolic geometry, we know that there is only one. We assume that basically we assume that gamma is a unique hyperbolic geodesic, but we found another curve in the same homotopy class with smaller lengths, and which is a contradiction. I don't know whether it makes sense, but well,
Let's prepare the questions for the rest of the week and see you again.